Alright, so today I'm talking about implicit differentiation. Well, first of all, why do we need implicit differentiation? Well, if we look at what we can do so far, we can use the power rule to deal with exponents of positive integers. We can use our knowledge of trigonometry. We can do some trigonometric derivatives. We can use the chain rule for compositions, and we can use the product rule, and of course, quotient rule as well. Well, how do we deal with things like this function where we have x's and y's mixed together? Well, we can't use product rule, and we can't really split this up in terms of y because we have it inside of a sign here. Well, we have to use implicit differentiation. And also, we don't know how to deal with logarithmic functions or exponential functions as of now. And all those formulas come from using implicit differentiation. Let's start off with an example to motivate this. The classic example is in circle, and I'm going to use that here. Well, if we look at our circle, if we want the derivative of this thing, or the rate of derivative of y with respect to x, we can simply rearrange. So y squared is equal to 5 minus x squared, and y is equal to plus minus 5 minus x squared. But you see that we have to deal with this in two branches now, and that's tedious, but we can deal with the positive branch first for today. So y is equal to 5 minus x squared dy dx is equal to, I'll rewrite this as 5 minus x squared to the power of half. So dy dx is half 5 minus x squared to the power of negative half multiplied by negative 2x, which is the derivative of the inside function. And this simplifies to negative 2x over 2 square root 5 minus x squared, which is negative x over square root 5 minus x squared. If we look back here, we said that y was equal to square root of 5 minus x squared, so we can say that this is actually negative x over y. And that's the derivative. Now let's look at how this process can be much simpler using implicit differentiation. Well, first of all, what we have to do is take the derivative of both sides with respect to x. Well, firstly, we know that the derivative of any constant is 0. And then on the left side, because the derivative operator is linear, we can split this up into two terms. And the first one is simply 2x using the power rule. And for the second, we have to use a chain rule because for us, y squared, y is implicitly defined as a function of x. So we have to deal with it as a composition of functions. So if you remember from the chain rule, if we had something squared, it would be 2 times something to the power of 1 multiplied by the derivative of something with respect to x. So it's precisely what we have to do here. It's just that y is there, so it looks a little weird, but it's essentially the same process. So first of all, derivative of outside would be 2y multiplied by the derivative of inside function, which is y, and that's dy by dx. And this is equal to 0. Now we simply have to solve for dy by dx. And we see that it is really the exact same result that we got earlier. But when you get smooth or faster with this method, it's much faster than chain rule, and we don't have to deal with two different cases. And of course, in a lot of the real functions that we'll meet, we can't simply isolate for y. For example, in this example, where the function is x cubed plus y cubed is equal to 6xy. Now, clearly, you still can if you use the cubic formula, but that's really messy, and nobody wants to do that. So using our newfound knowledge of implicit differentiation, we can deal with this in a much simpler way. So d by dx of x cubed plus y cubed is equal to d by dx of 6xy. For the first term, x cubed, it's simply 3x squared. And for the second term, derivative of outside is 3 times something squared, so 3y squared multiplied by the derivative of inside, which is dy by dx. Really, we can write this as y prime because in a lot of questions it gets really messy and you don't want to be writing dy by dx the whole time. So I'm going to color code it to make it simpler. And on the right side, we have to use the product rule. So if you remember, uv prime is equal to u prime v plus uv prime. So firstly, we differentiate x, so we get 1, so 6y plus, now we differentiate y, so 6x times 1 times y prime, because remember, chain rule. We have to have a term for the derivative of the inside. So now what we have to do is, we can move the like terms to one side. All the terms containing y prime, we can move to one side. So we get 3y squared y prime minus 6x y prime is equal to 6y minus 3x squared. And then we can factor out y prime. So we get 3y squared minus 6x is equal to 6y minus 3x squared. And now we can say that y prime is equal to 6y minus 3x squared all over 3y squared minus 6x. And that's it. That's sufficient. That's the form we are required to leave it in. Now for another example, which is really what it's more useful for, we can derive a lot of formulas that originally we can't do. For example, we know that the power rule is true for positive integer exponents because of the binomial formula, but we can generalize this to all real numbers. Well, we can't deal with all real numbers in one go, so we can start off with doing rational exponents. So rational numbers come in the form of m over n, where m and n are positive integers. So essentially what we want is the derivative of y with respect to x, where y is x to the power of m over n. So to start off, we want to get rid of this fractional exponent, and we can write this as y to the power of n if we just raise both sides to the power of n. So we get y to the n is equal to x to the m because of exponent rules. Now we can differentiate implicitly. On the left side, this is sloppy notation, but it's really more important to know what we're doing here. So on the left side, it would be n times y to the n minus 1 using the power rule, and then multiplied by the derivative of the inside. And then on the left side, on the right side, it's more simple, where we just have mx to the m minus 1. Because remember, m and n are positive integers, and we know how to deal with that using the power rule. Now, we isolate y prime. That's equal to mx to the m minus 1 over ny to the m minus 1. Now, usually this is sufficient, but for us, we want to find a general formula in terms of x. So we can substitute y for x to the power of m over n, and let's do that. So firstly, we can take out this constant. So the bottom becomes x to the m over n times n minus 1. And this is the same as x to the m over n times n is m. And then the second term, m over n times 1 is m over n. Now using exponent rules, we can combine this into a single power of x. So minus the entire bottom exponent, leaving expanding our bracket. The sign changes, so be careful. We get these two are gone, so we get m over n minus 1. And we can see that this is in fact the exact same power rule that we've known since the start. So we've shown that the basic power rule is also true for rational exponents, where again rational numbers can be represented in fractions in terms of integers. And so yeah, that's an application of implicit differentiation in order to find a general formula. And in the next video or the future videos, I'll be talking about how we can use implicit differentiation to do logarithmic differentiation, as well as finding formulas for exponential terms, like for example, a to the x, or e to the x, or ln x. And of course, if you enjoyed the video, make sure to like and subscribe and send this to all your friends who you think need help with different topics. And you can comment what you want to see next, and I'll try to do them. All right, thank you.